There is a problem in pure mathematics that a graduate student wrote down in 1999, and no one on Earth has solved it since. It is simple to state. You can describe what it asks for in a single sentence. Yet, 26 years of effort by some of the sharpest minds in physics and number theory, armed with supercomputers and proofs that run to 170 pages, have failed to settle it. What makes this riddle worth your evening is not the riddle itself. It is what has been quietly built on top of it. An entire reimagining of physical reality. A claim about whether there is a world out there at all when no one is looking, now rests on the assumption that this geometry problem has an answer. Pull the geometry out, and the philosophy underneath has nothing to stand on. The geometry is called a symmetric informationally complete measurement, a SIC-POVM. The unsolved problem is Zauner's conjecture, and the philosophy is QBism, the framework in which the equations of physics are not a description of the cosmos, but a manual for one observer's personal beliefs. Before the screen goes dark, you will understand what a SIC-POVM is, and why its perfect symmetry is so strange. You will see the single equation QBism puts in place of the law of probability. You will watch a simple question about measurement collapse into one of Hilbert's century-old problems. And you will see why the most observer-centered picture of reality ever proposed depends on a structure no observer invented. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, here is where it begins. The word measurement sounds simple. You point an instrument at the world, the instrument responds, and you read off a number. A thermometer reports a temperature. A scale reports a weight. In ordinary life, the measurement reveals something that was already there. The thermometer does not create the temperature, it discloses it. In quantum theory, this simple picture breaks down, and physicists have spent a century arguing about what replaces it. The most general way to describe any quantum measurement is a mathematical object called a POVM, a positive operator-valued measure. Strip away the technical language, and a POVM is simply a complete list of the possible outcomes of an experiment, each one represented by a mathematical operator, with the whole set required to account for every possibility, so that the probabilities of all outcomes sum to 1. Every measurement you can perform on a quantum system, no matter how exotic the apparatus, can be written as a POVM. It is the grammar of quantum questions. Within that vast space of possible measurements, one kind stands out for its symmetry. It is called symmetric and informationally complete. The name is a mouthful. The idea is elegant. Picture a quantum system described in a space of some number of dimensions, and call that number d. In ordinary quantum mechanics, d is just the count of distinguishable states the system can have. A single quantum bit, a qubit, lives in 2 dimensions. A more complex system lives in more. A symmetric, informationally complete measurement in that d-dimensional space is a set of exactly d-squared special states, arranged so that every one of them makes precisely the same angle with every other. Not approximately the same, exactly. The defining condition can be written as a single clean equation. The squared magnitude of the overlap between any two distinct states in the set equals 1 over the quantity d plus 1. Say it aloud. The squared overlap between any two distinct SIC vectors equals 1 over d plus 1. That value never changes. It does not matter which two of the states you pick. The relationship between them is fixed, rigid, and identical across the entire set. Mathematicians have a cleaner way to say this. A SIC is a maximal set of equiangular lines. An equiangular line is a direction in space such that the angle between any two of them is the same. In our ordinary three-dimensional world, you can only fit so many such lines before the geometry forbids more. In the complex space of quantum mechanics, the maximum possible number of equiangular lines in d dimensions is exactly d squared, a bound proven by Delsart, Goethals and Seidel in 1975. A SIC-POVM is the structure that reaches that maximum. It is the most symmetric arrangement of quantum states the geometry will permit. Hold on to the word symmetric, because the symmetry is the whole point, and it is the thing that will not let physicists go. Consider the simplest possible case, the qubit, where d equals 2. Then d squared is 4. A SIC-POV in 2 dimensions is a set of 4 quantum states. And there is a way to picture them that needs no equations at all. Every state of a qubit can be drawn as a point on the surface of a sphere, which physicists call the Bloch sphere. The 4 states of the SIC, placed on that sphere, point to the 4 vertices of a perfect regular tetrahedron inscribed inside it. 4 points, spread as evenly across the sphere as 4 points can possibly be, each one separated from the others by the same angle, the tetrahedral angle, the arc cosine of negative 1/3, about 109.5 degrees. This is worth sitting with. The simplest, non-trivial quantum measurement, written in its most symmetric form, is a tetrahedron, one of the 5 Platonic solids, the shape the ancient Greeks assigned to the element of fire. Perfect order, hidden at the foundation of a theory whose reputation is built on randomness. We will return to that order. For now, simply notice that it was not designed by the physicist. It was found there, waiting, when they looked for the most balanced way to ask a quantum question. Let the image settle, because it is the visual key to everything that follows. Picture a translucent sphere, faintly glowing, and inside it 4 points of light, each connected to the other 3 by lines of equal length. A tetrahedron suspended in glass, turning slowly. No matter how you rotate it, the symmetry holds. There is no special direction, no favored face. That balance is the whole meaning of the word symmetric. Now try to imagine what the same structure becomes in higher dimensions. The sphere is no longer an ordinary sphere, but a space of many complex dimensions the eye cannot picture. And the 4 points become 9, then 16, then thousands, then more than 1 billion. A constellation of directions so vast and so perfectly balanced that every pair, chosen anywhere in the swarm, stands at the identical angle. There is no way to truly see it. There is only the equation, holding the impossible arrangement in place. The squared overlap between any two, exactly 1 over d plus 1, forever. There is a grounding worth making here, because this is not abstract decoration. The qubit, the case where d equals 2, the tetrahedron in the block sphere, is the working unit of every quantum computer being built today, from the machines at IBM and Google to the ion traps in university basements. When engineers calibrate such a device, working out what state their hardware has actually produced, the symmetric measurement is one of the natural tools for the job, precisely because it is the minimal, complete reference. The tetrahedron is not a philosopher's daydream. It is the shape that the most practical quantum technologists reach for when they need to ask a real qubit with the fewest possible questions exactly what it is. What does it mean that the most efficient way to interrogate a piece of laboratory hardware is a structure whose general existence we cannot prove? The practical and the unprovable sitting in the same object. The deeper reason these structures matter is captured in the second half of the name, informationally complete. A SIC-POV contains exactly enough states to pin down any quantum state completely. If you know the probabilities that a SIC measurement assigns to each of its d-squared outcomes, you know everything there is to know about the system. Its entire quantum state can be reconstructed from those numbers and nothing else. Not one outcome too many, not one too few. The number d squared is exactly the number of independent quantities needed to specify a quantum state. A SIC is therefore minimal and complete at the same time. The leanest possible measurement that still tells you everything. It is, in a precise sense, the ideal reference experiment. Think about what that means with an analogy from ordinary measurement. Picture a master reference, a single, perfectly machined set of gauge blocks, against which every other length in a workshop can be checked. A good reference standard has two virtues at once. It is complete, in that any length you care about can be expressed in terms of it, and it is economical, in that it carries no redundant, wasted parts. Most measuring tools have one virtue or the other. The SIC-POVM has both, exactly, with nothing to spare. It is the master reference of quantum measurement, the yardstick against which any quantum state can be fully and minimally expressed. And there is an equation that makes this precise. The quantum state, written as what physicists call a density matrix, can be reconstructed as a sum over the d-squared SIC outcomes, each weighted by that same deformed quantity, the probability of the outcome multiplied by d plus 1 minus 1 over d times the corresponding measurement element. In other words, the full state of a quantum system is mathematically equivalent to a simple list of probabilities for a single SIC measurement. The abstract, complex-valued object physicists had wrestled with for decades becomes, in the presence of a SIC, an ordinary catalogue of betting odds. That equivalence is the seed from which the entire QBist program grows. It is also the reason the QBists needed the SIC to exist so badly. Without it, there is no clean dictionary between the state and a set of probabilities, and the whole reframing falls apart. What does it mean that the cleanest possible description of a quantum system, the one that turns its mysterious state into plain probabilities, exists only if an unproven geometric conjecture happens to be true? Hold the question. We are not ready to answer it. But notice it is already there, in the foundations, before we have said a word about philosophy. For most of the 20th century, these structures were a curiosity. Then, in 1999, an Austrian graduate student named Gerhard Zauner submitted a doctoral thesis at the University of Vienna with a title that translates as Quantum Designs. In it, he studied these maximally symmetric measurements, calling them maximal quantum designs, and he made a claim that has haunted the field ever since. He conjectured that a SIC-POVM exists in every finite dimension, not just in 2 dimensions or 3, or the handful that had been checked by hand, in every dimension, all the way up, without end. He went further. He proposed that in every dimension, the SIC could be generated in a particular, highly structured way, built from a single seed state by acting on it with a specific group of symmetry operations, and tied to a special symmetry now named after him, the Zauner symmetry. That claim is Zauner's conjecture. Stated plainly, for every dimension, the most symmetric possible quantum measurement exists. It sounds like the kind of thing that should be easy to prove or easy to disprove. It has been neither. Zauner's thesis was, for years, neither published in English nor widely read. The work circulated slowly, and an English translation did not appear until 2011. But the conjecture at its heart outgrew its origins and became one of the most stubborn open problems in quantum information. The community gave the structures their modern name in 2004, when Joseph Raines, Robin Bloom-Cohout, Andrew Scott and Carlton Caves published a paper coining the term SIC-POVM and computing numerical examples up to dimension 45. The hunt was on. Over the following years, researchers found SICs in dimension after dimension. Marcus Grassel and Andrew Scott built a systematic catalogue, computing solutions for every dimension up to 67, and producing what looked like a complete list of the symmetric solutions up to 50. Later, using a supercomputer named Chimera at the University of Massachusetts, Boston, Christopher Fuchs and his collaborators pushed numerical solutions all the way to dimension 151. Every time anyone looked in a new dimension, they found a SIC. Every single time. And yet, here is the strange part, the part we will keep circling back to. No one has ever been able to prove that the pattern continues forever. 26 years after Zauner wrote it down, the conjecture remains open. The evidence is overwhelming. The proof does not exist. Keep that gap in mind. A structure that always appears when you look for it, but cannot be shown to exist in general. We will need that tension later. Now we have to bring in the second half of this story, because the SIC-POVM did not stay a problem in pure geometry. It became the mathematical heart of a radical idea about reality itself. That idea is called QBism. The name began as a contraction of quantum Bayesianism, and the term was coined in 2009, though the framework is older. Its foundational paper was received in September 2001 and published the following year, written by Carlton Caves, Christopher Fuchs and Rudiger Schack, titled Quantum Probabilities as Bayesian Probabilities. To understand what they proposed, you have to understand the problem they were trying to solve. At the center of quantum mechanics sits a mathematical object called the quantum state, or wave function. The equations of the theory tell you how to use it. Feed in the state, turn the crank, and out come the probabilities of what you will see when you measure. The rule that converts the state into those probabilities is called the Born rule, written down by Max Born in 1926. In its standard form, the probability of an outcome is given by the trace of the state multiplied by the operator for that outcome. The mathematics is not in dispute. It has been confirmed to extraordinary precision for 100 years. What is in dispute, what has never been settled, is what the quantum state actually is. The mainstream view, in most of its forms, treats the state as something objective, a real description of a real system, out there in the world, independent of anyone observing it. On that reading, when a measurement happens, the state changes, the famous collapse of the wave function. And physicists have argued for a century about what that collapse physically is, an argument known as the measurement problem. QBism proposes a different answer, and it is a startling one. According to QBism, the quantum state is not a feature of the external world at all. It is a state of belief. It encodes a particular agent's personal expectations, their degrees of confidence about what they will experience if they act on the world in a certain way. On this view, the wave function lives in the mind of the user, not in the system being studied. Caves, Fuchs and Schack argued that the probabilities the Born rule produces are Bayesian probabilities, the same kind of personal, subjective probability a gambler assigns when placing a bet, updated as new information arrives. Follow what that does to the measurement problem. If the quantum state is only a catalogue of your personal expectations, then when you make a measurement and update it, nothing physical has collapsed. You have simply learned something and revised your beliefs the way anyone revises a forecast when the evidence comes in. Proponents of this view argue that the century-old puzzle of wave function collapse dissolves. There was never a physical collapse to explain, only an agent changing their mind. Rudiger Schack put one of the framework's core commitments bluntly in 2014. Another commonly held prejudice, he said, is that a probability 1 assignment implies the existence of an objective mechanism that brings about the event. In QBism, even certainty is a feature of the agent, not a guarantee about the world. The physicist N. David Mermin of Cornell, a respected and famously clear-headed commentator on quantum foundations, became one of the framework's most prominent later advocates. That was a notable conversion, because Mermin had spent years as a sharp critic of woolly thinking about quantum mechanics, and his arrival lent the program a credibility it had lacked. Fuchs coined a second term for the broader philosophy behind it: participatory realism, the notion that the agent is not a passive spectator of a finished reality, but a participant whose actions matter to how reality unfolds for them. The intellectual lineage runs back to John Archibald Wheeler, the American physicist who coined the phrase black hole, and who spent his final decades insisting that the observer plays an active role in bringing the physical world into focus. Wheeler called it the participatory universe and compressed it into a slogan: it from bit. The deeper roots run back further still, to a physicist named Edwin Thompson Jaynes, who, from the 1950s onward, argued that probability in physics should be understood as a measure of an agent's information rather than a property of the world. Jaynes was a precursor the QBists drew on before parting ways with him over technical details, replacing his approach with a theorem from the mathematician Bruno de Finetti. There is a piece of human history here worth telling, because it grounds the abstraction in a real life. Christopher Fuchs, born in Cuero, Texas, did much of his thinking in a vast, decades-long correspondence with other physicists. Thousands of emails arguing the foundations of quantum theory letter by letter. In May of 2000, the Cerro Grande fire swept through Los Alamos, New Mexico, and destroyed his home. Fuchs later said, half in earnest, that he had posted his entire correspondence to the public archive as a way of backing up his hard drive against exactly that kind of loss. That collection became a book, Coming of Age with Quantum Information, published by Cambridge University Press in 2011. And the framework took much of its public shape at the Perimeter Institute in Waterloo, where Fuchs gave the talk that put the word QBism into circulation. These are not fools chasing a fashion. They are serious people who looked at the strangeness of quantum theory and concluded, after decades of argument, that the way out was to make the observer central. That conclusion deserves the fairest possible hearing and the most rigorous possible test. One more voice from the history will matter later, because it names the very mystery this whole story turns on. In 1960, the physicist Eugene Wigner wrote a famous essay on what he called the unreasonable effectiveness of mathematics in the natural sciences. He confessed that the way abstract mathematics, invented for its own sake, keeps turning out to describe the physical world is something close to a miracle. It is difficult, Wigner wrote, to avoid the impression that a miracle confronts us here. Keep Wigner's miracle in mind. We are about to watch a piece of pure geometry reach down and touch the deepest unsolved problems in the theory of numbers. And when it does, Wigner's unease will stop being a philosopher's ornament and start being the center of the case. I want to be careful here, because this is the point of the video where it would be easy to take a side too soon. For now, I am only reporting what the framework claims, in the form its advocates would recognize as fair. QBism states that the wave function is personal. It states that probability in physics is subjective. It states that there is, in Schack's phrasing, no view from nowhere, no third-person, observer-independent description of reality that the equations are secretly about. These are strong claims, We will examine them, but not yet. What turns QBism from a philosophical position into a piece of hard mathematics, and what ties it back to the unsolved geometry we started with, is a single equation. The QBists call it the Urgleichung. The word is German. It means the primal equation, the original equation. To understand why it matters, and why it cannot be separated from the SIC-POVM, we have to look at it directly. Begin with a piece of ordinary pre-quantum probability that everyone already trusts, the law of total probability. Suppose you care about the outcome of some experiment, but instead of measuring it directly, you first run a different reference experiment and then reason about the final outcome based on what the reference told you. Classical probability gives an exact bookkeeping rule for this. The probability of the final outcome equals the sum over every possible result of the reference experiment of the probability of that reference result multiplied by the conditional probability of the final outcome given it. Say it plainly. The probability of J equals the sum over I of the probability of I times the probability of J given I. This is not exotic. It is the rule you use, without naming it, every time you reason, if it rains, then probably this, and if it does not, then probably that. Now, here is what the QBists discovered, and it is genuinely beautiful as a piece of mathematics. Take that reference experiment to be a SIC-POVM, the maximally symmetric measurement we spent the first part of this video describing. Then, quantum mechanics can be written as almost exactly the same bookkeeping rule, with one small, exact modification. The Urgleichung says that the probability of an outcome J equals the sum over the d squared SIC results, I, of a modified quantity, the probability of I multiplied by the factor d plus 1 minus 1 over d times the conditional probability of J given I. Spoken aloud, Q of J equals the sum over I of the quantity d plus 1 times p of I minus 1 over d times r of J given I. Look at what is different. The classical rule and the quantum rule are the same sum, the same structure, the same logic, except that where the classical rule has the raw probability p of I, the quantum rule has it stretched and shifted, multiplied by d plus 1, then reduced by 1 over d. That single deformation, that one little twist of an otherwise ordinary probability law, is the entire difference between the classical world and the quantum world, written in the language of belief. Everything strange about quantum mechanics in this formulation is compressed into those two constants, the factor d plus 1 and the term 1 over d. This is the equation in the title. This is QBism's equation. And notice what it requires. The Urgleichung is written in terms of a SIC-POVM. The reference experiment is a SIC. The whole elegant rewriting of quantum theory as a minimal correction to classical probability only works if a SIC-POVM is available to write it on, which means it only works in a given dimension if a SIC-POVM exists in that dimension. The QBist reformulation of physics, the one that is supposed to show that quantum theory is just normative reasoning for an agent, leans its entire weight on Zauner's unproven conjecture. We will come back to that. I promised you we would, and the promise is the spine of this whole story. There is a way to feel why the QBists prize this so highly. Quantum state space, the set of all possible states of a system, is a strange, curved, high-dimensional body, difficult to picture and harder to reason about in its native form. What the SIC-POVM provides is a coordinate system for that body, a way to assign to every quantum state an ordinary list of probabilities, the odds it gives to each outcome of the one reference measurement. Think of a cartographer facing the curved surface of the Earth and needing to put it on a flat sheet. A good map projection is a faithful dictionary between the round world and the flat page, letting you navigate one by reading the other. The SIC is that projection for quantum theory. It flattens the curved space of quantum states onto the familiar sheet of probability distributions, so that everything quantum can be rewritten in the plain language of likelihoods. This is why some QBists have called the SIC a kind of Rosetta Stone. It translates the unfamiliar script of the quantum state into the ordinary script of betting odds. And just as a map projection only works because the globe has a definite shape to be projected, the SIC translation only works because the geometry is really there, exact and fixed. The dictionary is only as trustworthy as the structure it is built on. Keep that thought close. It is the hinge on which the final argument will turn. So far, the picture is almost tidy. A beautiful symmetric measurement, an elegant equation built on it, a philosophy that uses both to argue the wave function is personal. If the story ended there, it would be a clean tale of mathematical physics. It does not end there. When researchers tried to actually construct these symmetric measurements, to write down the precise numbers that define the d-squared states in higher dimensions, the problem detonated. And what came out of it is one of the strangest connections in modern mathematics. To find a SIC, you only need one thing, a single starting state called the fiducial vector. The Zauner construction takes that one seed and generates all d-squared states from it automatically by acting on it with a set of symmetry operations, the Weil-Heisenberg group, the quantum generalization of the clock and the shift, the same algebra that underlies the famous uncertainty relations. The operations are called displacement operators, built from two basic moves, a shift that advances a state by one step, and a clock that multiplies it by a rotating phase. Apply these displacements to the single fiducial seed, sweeping through every combination, and you generate the entire orbit of d-squared states that make up the SIC. The whole symmetric structure, every one of its states, in every dimension, is encoded in that one seed vector, the way an entire crystal is encoded in the rule for stacking a single cell. So, the entire problem of building a SIC in any dimension reduces to finding the coordinates of that one fiducial seed. One vector. That is all you need. Find it, and the symmetry machine does the rest. Consider the scale of what that machine has to produce, because the numbers climb fast and they matter. In 2 dimensions, the SIC has 4 states. In 3, 9. In dimension 151, the symmetric measurement has 22,801 states, all of them at exactly the same angle to one another. In dimension 323, more than 100,000. By dimension 39,604, the number of mutually equiangular states exceeds 1.5 billion, over 1 billion directions in a complex space, every single pair separated by precisely the same angle. Picture trying to arrange 1 billion arrows so that no matter which 2 you pick, the angle between them is identical, to perfect precision, with no exceptions anywhere in the set. That is the constraint ASIC satisfies. It is an almost unimaginable degree of order, and the astonishing thing is that every time anyone has been able to check, the arrangement is there to be found. But found is not the same as proven, and the landscape of what is actually established is revealing. Mathematicians have constructed the SIC exactly, writing its coordinates in closed algebraic form, in a scattered, irregular list of dimensions. Every dimension up to 21, and then a patchwork of higher ones, 24, 28, 30, 31, 35, 37, and on, up through 124 and 323, with isolated peaks reached by the stark unit methods. Numerical solutions, high-precision approximations rather than exact formulas, exist in every dimension checked up to 151, and scattered far beyond into the hundreds and thousands. There is even a striking family that follows the Fibonacci and Lucas numbers, dimensions 4, 8, 19, 48, 124, 323, 844, where the structure behaves with special regularity. And there is a famous exceptional case in dimension 8, the Hogarth lines, a SIC of unusual beauty and symmetry. What you should notice about this list is what it is not. It is not a clean, infinite family with a proof attached. It is a heroic, dimension-by-dimension reconnaissance, a map drawn by sending climbers up one peak at a time, each ascent its own labor, with no general theorem guaranteeing the next summit is there until someone reaches it. What does it mean that we can climb every peak we attempt, yet cannot prove the mountain range continues? That is the shape of Zauner's conjecture, and it is the shape of the whole mystery. Then came the genuinely shocking part. To build a SIC, you have to find the coordinates of that one fiducial vector. And those coordinates are not simple. They are not fractions. They are not familiar constants like pi or the square root of 2. As the dimension climbs, the coordinates of the SIC become algebraic numbers of staggering complexity, solutions to polynomial equations of enormous degree, living in number systems that mathematicians have to construct with great care just to write them down. A problem that began as a clean question about angles in geometry turned, on contact, into a problem about the deep structure of numbers themselves. In 2016 and 2017, Marcus Appleby, Stephen Flamier, Gary McConnell and John Yard noticed a pattern in the numbers defining the known SICs. The special number systems in which those coordinates live were not random. They were a specific, celebrated kind of object in number theory, abelian extensions of real quadratic fields. Let me unpack that just enough to feel its weight. A real quadratic field is the system of numbers you get by taking the ordinary rational numbers and adjoining the square root of some positive whole number, the square root of 5, say, or the square root of 2. The SIC coordinates, it turned out, always lived in towers built on top of these fields, and the particular field was dictated by a clean formula, the discriminant, written as d plus 1 times d minus 3. Say it aloud. Delta equals d plus 1 times d minus 3. Hand the geometry a dimension, and the dimension hands you back a number-theoretic object, the field built on the square root of that discriminant. Here is why specialists nearly fell out of their chairs. Constructing these particular extensions, generating the precise numbers that build abelian extensions of real quadratic fields, is one of the oldest unsolved problems in all of mathematics. It is part of Hilbert's 12th problem, posed by David Hilbert in 1900 as one of his famous list of challenges for the new century. It is the modern form of a dream the great mathematician Leopold Kronecker called his Jugendtraum, his dream of youth. Mathematicians have wanted for over 100 years an explicit recipe for these numbers, and for the case of real quadratic fields, they do not have one. It is open. It is one of the unconquered summits of pure mathematics. And the symmetric quantum measurement, the SIC-POVM, the simple set of equiangular lines, the thing a physics graduate student stumbled into while looking for a tidy way to ask a quantum question, appears to be a doorway straight into it. Appleby and his collaborators wrote that the SIC problem and a solution to Hilbert's 12th problem for real quadratic fields should appear, on closer examination, to be intimately connected. The number theorist Ingemar Bengtsson, who has spent years on the problem, described it with restraint that barely conceals the astonishment. The SIC problem, he wrote, is easy to state, but soon reveals unexpected depths. And of the number-theoretic conjecture at its core, he said something a mathematician does not say lightly. It bears the hallmark of truth. What does it mean that a simple question about the angles between quantum states turns out to require the deepest unsolved machinery of abelian class field theory? No one knows. That is not a rhetorical flourish. It is the literal state of the field. As the physicist Blake Stacey put it, it is rather peculiar that the answer to a geometrical question turns out to involve advanced number theory. There is no accepted reason why the structure of quantum measurement should reach down and touch one of Hilbert's problems. It simply does. Sit with that for a moment before we go on, because it is the kind of fact that ought to unsettle a tidy worldview. And we will come back to ask what it implies. The story did not stop at a mysterious connection. It became a tool. Around 2018 through 2021, the number theorist Gene Kopp showed that if certain special numbers in these fields exist, units tied to the work of Harold Stark and the Stark Conjectures, themselves a refinement of Hilbert's 12th problem, then an SIC could actually be constructed from them. These Stark units are subtle objects whose logarithms are connected to the values of certain functions from the deepest parts of number theory. Kopp's method produced the first exact construction of the SIC in dimension 23, a dimension that had resisted exact solution. And the approach reached exact constructions in dimensions as high as 39,604. Then, on the 7th of January 2025, Marcus Appleby, Stephen Flamier, and Gene Kopp posted a paper of 177 pages, 130 pages of argument, and 47 of appendices, titled A Constructive Approach to Zauner's Conjecture via the Stark Conjectures. It is the closest anyone has come to cracking the problem. They introduced a strange new object they call a ghost SIC, built from the values of a deep number-theoretic function. And they proved that this ghost is a kind of mathematical shadow, Galois conjugate in the technical term, of an actual SIC, in every dimension above 3. In principle, it gives a construction of the symmetric measurement in all dimensions. But read the fine print, because the fine print is the whole point. Their construction is not an unconditional proof. It works only if two other things are true, and both of them are themselves unproven conjectures: the Stark conjecture for real quadratic fields, and a special identity about that deep modular function. The best result in 26 years of effort is a proof that rests on two deeper, unproven foundations. We have not reached bedrock. We have reached a floor that is itself suspended over a deeper unknown. What does it mean that the strongest argument for this structure's existence is a conditional one, true only if two other unsolved problems come out the right way? It is worth pausing on the sheer labor involved, because it grounds the abstraction in something human. Constructing these objects by computer search is brutally expensive. The mathematician Marcus Grasel reported that, for dimension 189, a search required roughly 23 million trials and about 3.5 years of computer processing time. For dimension 193, about 78 million trials and 13 years of processing time. The work scales viciously. The number of states grows as the square of the dimension d squared. So by dimension 323, you are managing 104,000 states. And by dimension 39,000, more than 1.5 billion. And still, for all that effort, the general proof does not come. When Andrew Scott and Marcus Grasel finished one of their great computational surveys in 2010, after finding solution after solution, they wrote a sentence that should be read slowly. We seem no closer to a proof of Zauner's conjecture than Gerhard Zauner was at the time of his doctoral dissertation. They noted that even the deep connection to the Weil-Heisenberg group, the symmetry that makes the whole construction work, appears to be born more out of luck than discernment. More out of luck than discernment. Hold that phrase. The people who know this structure most intimately confess they do not understand why it has the shape it has. One more comparison is worth drawing because it sharpens what makes the SIC special. There is a cousin of the SIC called a set of mutually unbiased bases, MUBs for short. Where an SIC is the most symmetric single measurement, MUBs are the most complementary set of measurements. Measurements so different that learning the answer to one tells you nothing about the others. The overlap condition for MUBs is 1 over D, where the SICs is 1 over D plus 1. Close, but not the same, and the difference matters. In dimensions that are powers of prime numbers, you can have at most D plus 1 mutually unbiased bases, and they are well understood. The SIC, by contrast, with its single condition and its D squared elements, remains stubbornly mysterious. Two maximal structures sitting side by side in the same quantum space, one tractable, one a portal into Hilbert's problems. We touched a moment ago on the broader QBist claim that the universe in some sense exists only for the observer. That is a story explored more fully on its own elsewhere. Here our concern is narrower and sharper, the geometry that claim is built on. It is worth seeing how this framework handles the sharpest puzzle in quantum foundations, because the QBists treat it as one of their proudest results, and it is a fair piece of the neutral picture. The puzzle is called Wigner's friend. Imagine a physicist, the friend, sealed in a laboratory, performing a quantum measurement and getting a definite result. Outside, a second physicist, Wigner, describes the whole sealed laboratory, friend included, with quantum theory. From inside, the friend has an outcome. The measurement is finished. The answer is one specific value. From outside, Wigner, who has not yet opened the lab, may still describe the friend as hanging in an unresolved superposition, no outcome yet fixed. Two physicists, the same event, two apparently contradictory accounts. For most interpretations, this is a crisis, because it seems to ask which description is the real one. QBism answers that the question is malformed. Because the quantum state is each agent's personal catalogue of expectations, there is no contradiction in the friend having an outcome, while Wigner still assigns a superposition. These are two different agents' accounts of their own anticipated experiences, not two competing descriptions of one observer-independent fact. In a 2020 paper, John de Broter, Christopher Fuchs, and Rudiger Schack put the principle this way. When two agents act on each other, each agent has a dual role as a physical system for the other, and, no user of quantum theory is more privileged than any other. The measurement, in this view, is radically local and first person. It is something that happens for the agent who performs it, where the agent touches the world, and nowhere else. This is genuinely elegant, and it is one of the strongest cards the framework holds. I lay it on the table at full value because the test we are coming to should be run against the framework at its best, not its weakest. There is a mathematical backbone underneath even this. The reason an agent's beliefs are not merely arbitrary, the reason two rational agents looking at the same system converge rather than drifting into private fantasies, was supplied by a result the QBists borrowed from the mathematician Bruno de Finetti, the quantum de Finetti theorem, which shows how shared data drives independent agents toward agreement. Even the subjectivity, in other words, is disciplined by theorems. Hold that thought. It will matter when we ask what exactly is doing the disciplining. And underneath all of it runs Wheeler's old provocation. John Wheeler, in a famous 1989 essay, wrote that every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, binary choices, bits, it from bit. Reality on this picture is assembled from acts of observation. Wheeler went further than even the QBists in some moods, suggesting that the only law of nature might be that there is no law, a phrase Fuchs has quoted with approval. Schack, building on the same intuition, has said plainly, "There are no laws that determine objective probabilities for measurement outcomes. The world does not evolve according to a mechanism." And Wheeler left behind a question he never answered, the one he said sat at the heart of everything. How come existence? He suspected that whoever followed the inquiry far enough would find, in his haunting phrase, their own puzzled face looking back at them. We will follow it far enough. We will see whose face is actually there. These are the claims laid out as fairly as I can state them. The wave function is belief. Probability is personal. There is no view from nowhere. There are no objective laws, only an agent's well-tuned expectations. The universe, in the strongest reading, waits on the observer. For 2/3 of this story, I have presented these ideas the way their advocates present them, because they deserve a fair hearing, and because the people who hold them are serious thinkers, not fools. Now the hearing is over. It is time to test whether the claims survive contact with their own foundations. Earlier, I told you to keep attention in mind, a structure that always appears when you look for it, but cannot be proven to exist. And I told you the QBist equation, the Urgleichung, is written on that structure. Now we collect on those promises. We are going to take the 3 boldest claims this framework makes and examine each one not against some outside objection, but against the very mathematics the framework is built from. That is the fairest test there is. A worldview should be judged first by whether it is consistent with itself. Begin with the central claim, the one that gives QBism its bite, that the quantum state is purely subjective, a personal belief, and that there is no objective reality underneath the physics for the equations to be about. This is the anti-realist heart of the framework. The wave function is in your head. The probabilities are your bets. There is, in Schach's words, no mechanism in the world that brings outcomes about. The world does not evolve according to a mechanism. The claim, stated at full strength, is that the apparent objectivity of physics is a kind of illusion projected by agents who reason well. Now examine it. Not the people, the claim. What does the claim actually stand on? It stands on the Urgleichung, the primal equation, the achievement that is supposed to show that quantum theory is nothing more than disciplined personal reasoning. And the Urgleichung, as we established, is written on a SIC-POVM. The entire argument that the quantum state is subjective is conducted in the language of a mathematical object, the symmetric measurement, whose defining property is that its overlap is exactly 1 over d plus 1, whose elements number exactly d squared, and whose coordinates are forced to live in specific number fields determined by Hilbert's 12th problem. Here is the contradiction, and it is not a small one. That symmetric measurement is not a belief. It is not subjective. No agent voted it into being. Whether a SIC-POVM exists in dimension 193 does not depend on what anyone expects, hopes, or bets. It depends on a fact about the geometry of complex space that is either true or false, independently of every mind in the universe. A fact so stubbornly mind-independent that 26 years of the cleverest agents alive have not been able to determine it by reasoning. The framework that says there is no objective structure underneath physics builds its flagship equation on exactly such a structure. The subjectivity of the state is parasitic on the objectivity of the geometry. This is a reductio, the argument turning on itself. If the QBist is right that nothing objective lies beneath physics, then the SIC-POVM is just one more subjective belief, and the Urgleichung is a statement about the agent's psychology, true by stipulation, explaining nothing about why the world is quantum. But if the SIC-POVM is what mathematicians plainly treat it as, a discovered mind-independent truth, met with surprise, resisting proof, bearing what Bengtson called the hallmark of truth, then there is an objective, rational structure underneath physics after all, and the central anti-realist claim is false. The framework cannot have it both ways. Its own equation forces the choice. And here is the part that should make any honest inquirer stop. The QBists, to their credit, do not entirely hide from this. Rüdiger Schach has acknowledged that the existence of SICs in all dimensions would strengthen the case for QBism. Read that carefully. The case for the view that reality is subjective would be strengthened by the truth of an objective mathematical theorem that no subject can establish. What does it mean that the strongest argument for the world being in your head is the existence of a structure that is provably not in your head? The admission gives the game away. The agent-centered cosmos is leaning with its full weight on a Platonic object, a rational order that exists whether or not any agent ever computes it. Consider an everyday version of the same mistake, because the logic is easier to feel than to state. Imagine an architect who insists, sincerely, that buildings have no objective structure, that a building is nothing more than the experience each visitor has of it, that there is no fact about the beams and loads independent of anyone walking through. It is a provocative philosophy, and over coffee it might even sound deep. But notice what the architect did to convince you. He drew a blueprint. He computed the load on a beam using numbers that did not care what he believed. He relied on the steel behaving the same way for everyone, every time, whether observed or not. The moment his philosophy needed support, he reached for exactly the objective structure his philosophy denies. The blueprint refutes the speech. And in QBism, the SIC-POVM is the blueprint. The framework reaches for an objective, agent-independent mathematics at the precise moment it wants to deny objective, agent-independent reality. That is where the everyday picture breaks, and the place it breaks is the place the claim breaks. What the evidence actually shows is the opposite of anti-realism. It shows a rational order that precedes the observer. The number fields were not invented to fit a desired conclusion. They were stumbled upon with astonishment by people who expected something simpler. The exact value, 1 over d plus 1, was not chosen for convenience. Deviate from it by any amount, and the structure is no longer ASIC. The discriminant formula, d plus 1 times d minus 3, was not legislated. It was discovered, the same across every dimension. This is not the signature of a convention agents agreed upon. It is the signature of something found, a structure that was already true before any mind arrived to be surprised by it. And a rational order that exists independently of every finite mind is precisely what points beyond finite minds, toward a mind in which such order is grounded. That brings us to the second claim, Wheeler's most radical, echoed by Schack, that there are no laws of nature at all. Law without law. The world does not run on a mechanism. There are only agents and their well-calibrated expectations. Let us examine this one too against the mathematics, and here the right move is simple inversion. Take the claim and turn it to face the evidence it is supposed to explain. If there were truly no objective law, no mind-independent order, then the structure of SICs across dimensions should be a patchwork, arbitrary, ad hoc, different in kind from one dimension to the next, with no reason for any of it. That is not what we find. What we find is the opposite of lawlessness. We find that in every dimension, the symmetric measurement obeys the same exact overlap condition. We find that the number field it requires is dictated by one clean formula applied uniformly across all dimensions. We find that these objects link systematically and without exception to one specific province of number theory, the ray-class fields of real quadratic fields, as if a single deep principle were threading through every case. law without law is precisely the claim data most flatly contradicts. The interlocking, exact, universal relations among SIC-POVMs are the very definition of law-like order, mind-independent, dimension-spanning, and so rigid that it has resisted every attempt to bend or break it. You cannot point at one of the most tightly constrained mathematical structures ever studied and call it evidence that there are no constraints. This is the fine-tuning argument in an unusually pure form, stripped of any appeal to cosmology or biology. We are not talking about the strength of gravity or the mass of an electron, quantities one might wave away as brute facts. We are talking about exact mathematical relations that could, in the space of logical possibility, have been otherwise, and are not. The overlap is exactly 1 over d plus 1. The count is exactly d squared. The field is exactly the one built on the square root of d plus 1 times d minus 3. Precision of this kind, exact, non-arbitrary, interlocking across an infinity of cases, is not what you expect from a world without order. Precision requires decision, and decision requires a mind capable of making it. Let me put this as plainly as I can with the oldest argument there is. When you find a precision instrument, a watch, a telescope, a finely cut key that turns one specific lock, you do not need to have watched it being made to know it was made. You read the maker's attributes off the product, the intelligence that planned it, the knowledge of materials, the intention behind every dimension. The inference from product to maker is one we trust constantly and rationally. Now look at the SIC-POVM with that same honest eye. It is a structure of staggering precision, a billion directions held at one exact angle, coordinates tuned to live in precisely the right number field, every relation interlocking with every other across infinite dimensions, and the whole thing so deep that proving it exists drags in the unsolved heights of number theory. If a far simpler precision than this, in a watch, compels us to infer a watchmaker, what does intellectual honesty require when we meet a precision incomparably greater, woven into the bones of mathematics itself? The materialist asks us to believe that the most exquisitely ordered structure ever studied is simply there, brute, for no reason, the product of nothing. That is not a conclusion drawn from evidence. It is a refusal to draw the conclusion the evidence points to. And now Wigner's miracle comes due. Remember his unease that mathematics invented in the abstract keeps turning out, inexplicably, to describe the physical world. Here that miracle reaches its most acute form. A question about the angles between quantum measurements, physics, turns out to be answerable only in the language of Hilbert's 12th problem, the purest, most abstract number theory, developed by mathematicians who had no thought of physics in their heads. Why should the deep structure of numbers, contemplated for its own sake, be the very thing the physical world requires to define its most symmetric measurement? The materialist has no answer. He can only call it a brute coincidence and move on. But notice what the theist's picture predicts. If one rational mind is the ground of both the physical order and the mathematical order, if the same intelligence underlies the structure of numbers and the structure of the world, then of course they fit. Of course, the abstract reaches down and clasps the physical. They were never two separate things meeting by luck. They are two faces of one rational order. Wigner's miracle is only a miracle if you assume the two orders are unrelated. Grant a common source, and the miracle becomes exactly what you would expect. Take a moment with that before we go on. Ask yourself honestly, which is the simpler explanation for a quantum measurement that secretly encodes century-old number theory? That two unrelated domains happen, for no reason, to be the same, or that one rational source underlies them both? Do not answer quickly. The whole weight of the case rests on which way an honest mind leans here. There is a contrast worth drawing, because physics offers a competing move when it meets order it cannot explain, and QBism, to its credit, refuses that move. Faced with the fine-tuning of the cosmos, some cosmologists invoke a multiverse, an unobserved infinity of other universes with other constants, so that ours, by chance, is one of the rare livable ones. Set aside for now whether that is good science. Notice only that it is an attempt to dissolve apparent design into an ocean of chances. But that escape is not even available here. You cannot wave away the SIC's order by imagining other mathematics in other universes. Mathematical truth is not local to a universe. The overlap condition 1 over d plus 1, the discriminant d plus 1 times d minus 3, these are not facts about our cosmos that might have differed elsewhere. They are necessary truths, the same in every possible world. There is no multiverse of arithmetic to hide the precision in. The order stands exposed, with nowhere to disappear, demanding to be explained rather than diluted. Here, someone will reach for the most common escape, and it deserves a direct answer. The escape is, give it time. Mathematics has solved hard problems before. Zauner's conjecture will be proven eventually. The number theory will be understood, and the mystery will evaporate. This is the promissory note, the faith that the future will deliver what the present cannot. But look honestly at the track record. 26 years. Some of the best minds in two fields. Supercomputers running for years on a single dimension. And the strongest result, the 170-page achievement of 2025, is not a proof but a conditional. It works only if two deeper, unproven conjectures hold. It will be explained eventually is not an explanation. It is a description of what one hopes to one day possess. And even if the proof arrives tomorrow, it would tell us that the structure exists. It would not tell us why this structure, why this order, why a quantum measurement should encode Hilbert's century-old dream. Proving that a thing is so is not the same as explaining why it is so. The deepest question would still be standing. Notice where the chain of explanation runs, because this is the infinite regress argument made concrete and specific. The existence of the SIC is made to rest on the Stark conjecture. The Stark conjecture sits inside Hilbert's 12th problem. Each layer is justified by appeal to a deeper layer. This is exactly the structure of a chain of dependent reasons. Each link borrowing its authority from the one below it. A chain like that cannot hang in the air forever. Either it terminates in something that is not borrowed, something whose order is grounded in itself, or the whole chain is suspended over nothing and explains nothing. The mathematics is telling us, in its own austere language, that the rational order it keeps uncovering points downward toward a foundation it cannot itself supply. What grounds the order that grounds the order that grounds the SIC? The equations do not answer. They were never going to answer. That question is not a mathematical question. It is a metaphysical one, and it has a metaphysical answer. Now the third claim, the one that draws the headlines, that the observer creates reality, that nothing is definite until an agent acts, that the participatory universe waits on us, that there is no world independent of the experiences of the observers within it. This is the claim people hear and find either liberating or vertiginous. It is also the one most easily misread. So let us be careful and, above all, fair. First, what the framework does not say. It does not say solipsism, the doctrine that only you exist and everyone else is a figment. The QBists are emphatic on this, and they are right to be. N. David Mermin answered the charge directly. Facile charges of solipsism, he wrote, miss the point. His reasoning is worth hearing, because it quietly concedes something enormous. My experience of you, Mermin said, leads me to hypothesize that you are a being very much like myself, with your own private experience. Read what that sentence assumes. It assumes a real you, a second center of experience the speaker did not create, encountered out in the world and must reckon with. The moment the framework defends itself against solipsism, it admits a reality beyond the single agent. It admits the world kicks back. That admission is fatal to the strong reading of observer-created reality. And it is fatal from the inside. Examine the logic. If my measurement creates my reality, and your measurement creates yours, and yet I must hypothesize you as a being like myself, whom I did not create, then there is something real that is not the product of my participation. There is a world that does not wait on me. The participatory picture, pressed for consistency, does not give you a cosmos conjured by observers. It gives you observers embedded in a reality larger than any of them, a reality that presents each of them with the same stubborn order, the same physics, the same quantum theory, the same symmetric geometry with its overlap of 1 over d plus 1. The kickback the agent feels has a structure, and the structure is the very mind-independent order we have been tracking all along. Even the framework's own intellectual neighbours balk at the strong reading. Roger Penrose, no enemy of bold ideas about mind and physics, called the strongly participatory notion barely credible. Carlton Caves, one of the three founders, the C in the foundational paper, no longer counts himself a QBist. When a co-author steps away from the strongest form of the claim, and a thinker as adventurous as Penrose calls it barely credible, that is not proof the claim is false. but it tells you the claim is doing more work than its own evidence can bear. What does it mean that the picture of a universe summoned by observers cannot keep its own founders fully on board? Let me give this claim its due, because there is something real in it that the materialist has no answer for. Strip away the overreach, and participatory realism is pointing at a genuine fact that physics, in its deepest formulation, cannot get rid of the observer. The agent who measures, who experiences, who holds beliefs and updates them, sits irreducibly at the center of the theory. Fuchs puts it that reality is more than any third-person perspective can capture. Notice the wording: more, not less. The QBists are not nihilists denying the world. They are insisting that any complete account of reality has to make room for the first person, for the experiencing subject, for mind. And on that narrow point, the evidence is with them, and against the materialist who promised that mind would turn out to be nothing but matter in motion. Here is the question the materialist cannot answer, and the QBists, almost despite themselves, have walked us straight to it. A purely material universe, atoms, fields, equations grinding forward with no one home, has no place in it for an observer in the deep sense the theory requires. Matter does not have a point of view. A field has no first-person experience of being measured. Yet the most successful physical theory ever devised cannot be written down in its most elegant form without an agent at the center, someone whose beliefs the Urgleichung describes, someone for whom the measurement is an experience. Where did that observer come from, in a universe that materialism says is fundamentally observer-free? Consciousness, the very thing the agent brings to the participatory picture, is precisely what unconscious matter cannot produce and cannot explain. Arrangements of particles do not start to feel. The framework foregrounds the conscious agent and then offers no account of where consciousness could come from in a merely material world. That gap is not a weakness of QBism, it is a clue. A cosmos that genuinely requires mind at its foundation is a cosmos that points beyond matter toward a mind that was there first. Now we can collect the debt the framework left unpaid earlier. Remember the quantum definiti theorem, the result that disciplines the agent's subjective beliefs, that keeps rational observers from drifting into private fantasy and pulls them toward agreement. Ask the simple question the QBist tends to hurry past. What is doing the disciplining? If reality were genuinely just a marketplace of personal beliefs with no objective structure beneath, there would be nothing for the agents to converge on, no reason their independent guesses should ever meet. But they do meet. They are driven toward the same physics, the same Born rule, the same symmetric geometry, because there is something there, mind-independent and the same for all of them, that their beliefs are beliefs about. The very mechanism the framework uses to rescue itself from solipsism is a mechanism that presupposes an objective order the agents are tracking. Subjectivity that reliably converges is not evidence against objective reality. It is evidence for it. Consider one more picture from ordinary life, because it captures the whole shape of the error. Think of a child learning her native language. In one real sense, she is an active participant. She babbles, experiments, makes the words her own, and no one can do it for her. You could be forgiven watching her for thinking the language lives entirely in her, that she is building it from the inside. But press that thought and it breaks, and the place it breaks is exactly the point. The grammar she is converging on was not invented by her. It was there before she was born, a structure she is discovering, not authoring. Which is precisely why another child across the city, participating just as actively, arrives at the same grammar rather than a different one. Her participation is real, her authorship is not. And that is the exact shape of the observer in QBism. The agent genuinely participates, measures, experiences, updates. But the order the agent meets, the symmetric geometry with its exact angle and its number-theoretic depths, was laid down before any agent arrived, which is why every agent meets the same one. Participation is real, authorship is an illusion, and a grammar no speaker invented points to a mind that composed it. What would you conclude from this evidence if you followed it honestly and let no prior commitment decide the verdict in advance? A framework built to make the observer central keeps running into a structure the observer did not make. At every level, the geometry, the equation, the convergence of beliefs, the requirement of consciousness itself, the same finding repeats. There is a rational order here that precedes us, exceeds us, and does not answer to us. The honest name for the source of an order like that is not chance, and not the observing mind that arrives to find it already in place. The honest name is an intelligent cause. I want to step back for a moment and speak plainly, because I have sat with this material for a long time and something about it does not leave me. It is not the difficulty of the conjecture that stays with me, nor the cleverness of the equation. It is the direction everything leans. Here was a research program built deliberately to dethrone the objective world, to show that physics is about agents and their expectations, that there is no cold structure out there indifferent to us. And the more rigorously its champions pursued it, the more they were forced to lean on a structure that is exactly that. Cold, exact, indifferent, out there, unmade by anyone. They did not want to find a mind-independent order. They went looking for the opposite. They found it anyway because it was already there. What does it mean when even the attempt to abolish objective order ends up resting its whole weight on objective order? Recall Wheeler, who started so much of this, and his question at the heart of everything: how come existence? He guessed that anyone who chased the inquiry far enough would meet, in the end, their own puzzled face looking back at them, the observer, reflected in the riddle. But that is not quite what we found when we followed it all the way down. Past the observer, past the agent's beliefs, past the participatory slogans, the inquiry did not terminate in a human face. It terminated in a structure no human face composed, a perfect, unprovable order waiting in the dark. What does it mean that the deepest look into the most observer-centered physics ever written shows us, finally, not ourselves, but something that was there before us? The face in the riddle is not the agent's. There is a deeper reflection behind it. So let us render the verdict, and let us render it on the evidence, because the evidence has been remarkably one-directional. We came looking for the most observer-centered, most anti-realist, most agent-built picture of physics ever seriously proposed. We found that it cannot stand on its own. Its central equation is written on an object it cannot account for. Its denial of objective structure is refuted by the objective structure it depends on. Its denial of law is contradicted by the most rigid lawful order in mathematics. Its dream of a universe summoned by observers collapses on its own logic into observers who find themselves inside a reality they did not make. At every turn, the framework reaches for a rational, mind-independent order, exact, discovered, resisting every attempt to prove or dissolve it. And that order is exactly what a world of mere matter cannot supply, and a mind can. This is the part that stays with me. Not the difficulty of the conjecture, the direction it points. The most strenuous effort in modern physics to put the human observer at the center of reality ended up demonstrating, against its own intentions, that beneath the observer lies a structure no observer created. You can feel the framework straining to keep the mind in charge, and you can watch the mathematics quietly insist that the mind arrived late into an order already laid down. The order was there first. The question this whole story leaves us with is not whether that order exists. 26 years of failed proofs are testimony that it does, and that it does not bend to us. The question is, what kind of thing the ground that order must be? And a rational order that holds across infinite dimensions, that no mind invented and no mind can fully reach, that bears, in a mathematician's careful word, the hallmark of truth, such an order is the fingerprint of intelligence, not the residue of accident. The evidence points one direction. It has pointed there the whole time. Let me bring this exploration to a close. We began with a single unsolved problem, Zauner's conjecture, the claim that a symmetric, informationally complete measurement, a SIC-POVM, exists in every dimension. We watched that geometric question grow into the foundation of QBism, the framework that treats the quantum state as personal belief and writes all of physics into one primal equation, the Urgleichung. And we watched that equation, and the philosophy resting on it, reach down through the discriminant formula into the ray-class fields of real quadratic fields, into Hilbert's 12th problem, into the oldest dreams of number theory, a structure exact to the last digit, discovered and not invented, unproven after 26 years, and unbending to every mind that has approached it. And when we tested the boldest claims built on that geometry, that reality is subjective, that there is no law, that the observer makes the world, each one broke against the very mathematics it stood on. The anti-realist equation is written on a Platonic object. The denial of law is refuted by an iron lawfulness. The observer-made universe dissolves into observers inside an order they did not author. What survives the examination is not the absence of an objective world, but its quiet, insistent presence, a rational structure that was already true before anyone looked, and that points beyond every finite mind to the mind in which such order is grounded. Science can describe how the SIC behaves. it cannot tell us why such an order exists at all. That question lies on the far side of every equation, and it has only ever had one rational answer: an intelligent cause, with knowledge enough to ground a structure mathematicians cannot exhaust, and will enough to make it exact. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. There is a thread we only half followed tonight: the larger QBist claim that the universe in some sense exists only for the observer, that reality is something you participate in rather than merely witness. We held it at arm's length here because tonight our subject was the geometry beneath it. But if that idea took hold of you, I have followed it much further down its own road. You will find where on the end screen and in the description. The most agent-centered vision of the cosmos ever written rests in the end on a truth no agent created, a perfect, unproven order that was waiting in the dark long before there was anyone to find it, and will be waiting still long after. Good night.